Hi, now we are going to talk a new chapter, oscillations. Very important topic here is simple harmonic motion and equations for displacement, velocity, acceleration, graphical representation, etc. So to start with, we will do periodic and non-periodic motion. The motion which repeats at regular intervals of time, we call it as periodic motion. The motion which repeats at regular intervals. What is the meaning of regular intervals? Heartbeat, 72 beats per minute. It happens at regular intervals. It is an example of periodic motion. Revolution of planets around the sun. It is an example of periodic motion because it happens at regular intervals of time. Non-periodic motion means motion which does not repeat at regular intervals. Motion which does not repeat at regular intervals, we call it as non-periodic motion. Example, motion of a vehicle, vehicular motion. You cannot say that it happens at regular intervals of time, the movement of vehicle. So that is called non-periodic motion. Okay, next, oscillatory motion. Oscillatory motion. To and fro motion. To and fro motion, we call it as oscillation. To and fro, which happens periodically. Oscillation of a pendulum. To and fro. It happens at regular intervals of time. So we can say oscillatory motions are periodic in nature. Converse is not true. All periodic motions are not oscillatory, but all oscillatory motions are periodic in nature. Okay. So this is basic definition of periodic, non-periodic, and oscillatory motion. Okay, next, harmonic function. Harmonic function means periodic function that can be expressed in terms of sine or cosine wave. Periodic function can be represented either by a sine wave or a cosine wave. That is called harmonic function. Non-harmonic means it is not represented by a sine or cosine wave. That's all. That is called non-harmonic. What is the meaning of that harmonic function? That how we are expressing. We will discuss simple harmonic motion. Through that, we will explain that harmonic function. Simple harmonic motion. Suppose you take a pendulum. You are accelerating it. That means you are displacing by a smaller angle, making an angle theta. The displacement is x. Or y also you can take, no problem. General representation. So you are displacing it. When you leave it, it accelerates in the opposite direction. So the acceleration proportional to displacement or acceleration is equal to a constant omega square into x. What is that omega square, sir? Time being, we will take that is a constant. We will prove that one later. So acceleration proportional to displacement. Why there is a negative sign? You are displacing the body in one particular direction. When you leave it, it moves in the opposite direction, accelerates in the opposite direction. So displacement one direction, acceleration in the opposite direction. So there is a negative sign. You can very well write in terms of force also. F is equal to ma. F is equal to a is minus omega square x. So minus m omega square x or f proportional to x. Either a proportional to x or f proportional to x, both are simple harmonic only. Okay. Right. Now, acceleration F is equal to ma. A is equal to F by m. We have another definition of force. F is equal to minus kx, where k is called force constant or spring constant. Anything you can say. In that case, you can write minus kx by m. That is also called acceleration. In terms of force constant, or if you are using a spring, in terms of spring constant, we can express F is equal to minus kx. Then acceleration is F by m. F is minus kx by m. This is also acceleration. A is equal to minus omega square x. Okay. So simple harmonic motion states that the body is set to oscillate. The body is displaced. The displacement is directly proportional to acceleration and always directed towards fixed points. Fixed point means center point here. Always directed towards a fixed point. It comes back to the center again and again. So the word always directed towards fixed point should be there. Okay. Simple harmonic motion, what are the examples there? Oscillation of a pendulum, vibration of a tuning fork, vibration of a tuning fork. When you strike the tuning fork in a rubber pad, then it sets into vibration. Oscillation of a balance wheel of a watch. Simple harmonic. Okay. Now, body is vibrating from the mean position again and again. That is called simple harmonic motion. Vibrates. Oscillation also we have seen. Particle vibrating from the mean position again and again. Simple harmonic motion. So using that, we can define few functions or few quantities. Displacement, definitions of s.e.a. Displacement, amplitude, time period, frequency, angular frequency, phase difference, initial phase. Displacement of a vibrating particle. Consider a body or a particle moving in a circular path. After a time of t seconds in that circular path, it is starting here, moving in anti-clockwise direction. This is after some time t. So initial point, final point. This is the displacement x or y you can take. No, sir. Particle is moving from here in clockwise. Draw a perpendicular. Final point. Draw a perpendicular. This is called a displacement. Amplitude. Maximum displacement of the vibrating particle. Suppose this is a sine wave. Maximum displacement of the vibrating particle, we call it as amplitude. This one or this. Maximum displacement. Time period. Time taken by the vibrating particle to complete one vibration or to complete one oscillation. Time taken by the vibrating particle to complete either one vibration or one oscillation. Simple pendulum experiment you are doing in practical, sir. You are taking 10 oscillations. You are measuring the time. Say for 50 centimeter length, you are getting 14 seconds. 10 oscillation, 14 seconds. Time taken for one oscillation is what? 14 by 10. So T is equal to 14 by 10, 1.4. This 1.4 we call it as time period. Frequency is called 1 by T. 1 by time period we call it as frequency. Time by number of oscillation is time period. Reverse number of oscillation per second. Convert into second because that is SI unit. Number of oscillation per second we call it as frequency. Next, angular frequency. Angular means omega. You know very well omega basic formula 2 pi by T. 1 by T we call it as frequency. So I can write 2 pi f. Angular frequency is 2 pi f. F is a frequency, that is 1 by time period. Okay. Next. Phase. Phase means the position of the vibrating particle, that is where it is situated after a time of 3 seconds. How much angle it is passing through. It is moving in circular path. Initial point, final point, what angle it is made. That is called phase. Phase means angle. From the initial to final. The angle subtended by the vibrating particle when it is executing simple harmonic motion. Phase difference. Phase difference means you have to consider two particles. Consider one particle moving in clockwise direction, another particle moving in anti-clockwise direction. So clockwise, anti-clockwise. The phase difference is 180 degree. That means out of phase. These two moving opposite. Opposite means out of phase, 180 degree. Both particles moving in the same direction at the same time, sir. Phase difference is 0. So phase difference means minimum two particles you need. The difference in angle, the difference in phase between the two vibrating particles, which is executing SHM. Initial phase, other name FO. Sir, displacement x or y you take, no problem, anything. Displacement. The equation for simple harmonic motion is y is equal to a sin omega t plus phi, phase difference. Phi naught, if we put, that is called initial phase. At time t is equal to 0, what is the phase of the vibrating particle? I don't understand, sir. Sir, particle starting here, it is starting in anti-clockwise direction. From here only you have started your measurement. Point A, only you have started your measurement. Then this is called initial phase, phi naught. Theta naught I will put, sir. You can put theta naught. At time t is equal to 0, at that time only I have started measuring, but the particle started its motion before itself. So at time t is equal to 0, the initial phase is phi naught. So the particle is starting only at A. Then what is the initial phase? Initial phase is 0. It depends how you are taking. Okay, fine. Now, equations for displacement, velocity, acceleration. Equations for displacement, velocity, and acceleration for a particle executing SHM. Particle moving in a uniform circular motion. Particle is moving in uniform circular motion, that is called as SHM. How a particle moving in uniform circular motion is SHM, sir? Consider a circular path. Particle is moving here. Particle vibrating from the mean position above and below or to and fro only, we call it a simple harmonic motion. Acceleration proportional to displacement. We saw in the definition. Particle is moving here. Different positions, you find the projection of the particle. Projection means you drop a perpendicular. That's all. At different points. Here it is starting 1, 2, 3, 4, 5, 6, 7, 8 positions we will take. You drop a perpendicular. Here it is starting, drop a perpendicular. It is moving in anti-clockwise direction. Here, perpendicular. Here, perpendicular. Here, perpendicular. Everywhere you put a perpendicular. Particle is moving in circular path, but when you drop a perpendicular, you can say here and here it is opposite. That means what? It is moving up and down. When a particle is moving in circular path or circular motion, the projection of the particle executing above and below to and fro motion from the mean position. So it is called a simple harmonic motion. Okay. Now, how to derive the equation? Center O, y dash, x dash. Particle is moving from the point Y. After a time of t seconds, this is the final point P. Join. This is radius R. No, sir. Radius small, capital A only I will write. Small. Capital A, you take it for acceleration. Small a, you take it for radius of the circular path. Okay. So, small a. You drop perpendicular here and here. It is making an angle theta. If this is theta, means vertically opposite, this is also theta. So, initial position, final position. A, take it as AB1. PQ. P already have taken. Q. So, initial point, final point. This is called the displacement Y. The displacement only we are going to calculate now. How to calculate? Displacement Y calculation. From triangle POQ, calculate sin theta. What is sin theta? Opposite side OQ by hypotenuse OP. OQ by OP. OQ is Y. OP is A. So Y is equal to A sin theta. We know omega is equal to rate of change of displacement. Angular displacement. Rate of change of displacement means velocity. Rate of change of angular displacement means angular velocity. In terms of rotational, in terms of circular path only, omega term will come. So theta is equal to omega t here. Substitute. Therefore, y is equal to a sin omega t. Equation 1. This is called the equation for displacement. A is called the radius of the circular path in which the particle is moving. Velocity. V is equal to, if you differentiate displacement, you will get velocity. Differentiation, basics, already mathematics you would have studied. Differentiation of sin theta is cos theta. Differentiation of cos theta is minus sin theta. So in this case, differentiate y. What is y? A sin omega t. So V is equal to, take A outside. Differentiation of sin omega t is cos omega t. Omega t, t is the variable here. Omega is a constant. So when you differentiate omega t, you will get omega. Sin 2 theta differentiation is cos 2 theta, sir. You cannot leave it as it is. Cos 2 theta into 2 theta differentiation is 2. Like that. A sin omega t, A constant, take it out. Sin omega t differentiation is cos omega t. Omega t differentiation is omega. That you have to take. A omega cos omega t. Acceleration. Acceleration. Capital A. Rate of change of velocity, we call it as acceleration. Rate of change of velocity. Rate of change of displacement is velocity. Rate of change of velocity, you call it as acceleration. So A is equal to, differentiate this A omega cos omega t. Differentiate. What will you get? A omega constant. Take it out. Differentiation of cos omega t. My cos theta differentiation is minus sin theta. So I will get minus sin omega t. Into omega t differentiation, omega. So you will get omega square. Correct, Amma? So acceleration is minus omega square. What is the formula? A sin omega t. A sin omega t is nothing but y. So minus omega square y. While defining simple harmonic motion, we have discussed acceleration proportional to displacement with a negative sign. Here we have a negative sign. So this is called simple harmonic motion. So displacement, velocity, acceleration. Sometimes we can represent acceleration like this also. Acceleration is rate of change of velocity d by dt of, what is velocity? Dy by dt. So I can write d square y by dt square. Acceleration A or d square y by dt square, both are correct. Substitute implies d square y by dt square is equal to minus omega square y. D square y by dt square plus omega square y is equal to 0. This is a condition for simple harmonic motion. In maths, we call this as differential equation. This is differential equation of SHM, simple harmonic motion. D square y by dt square plus omega square y is equal to 0. Y you call it as displacement of the particle executing SHM. Omega is a constant. Angular velocity, that is a constant. Okay. Now, sir, you told something about harmonic function. Representing this by a sine wave or a cosine wave. How will you represent? We will write.